Yeah, so so in this equation we have already seen that how to find the solution of the homogeneous part. Now we are considering the how to solve how to find the particular solution of the non-homogeneous equation. And for that we discussed in the previous lecture uh, this result, which says that if we have two solutions y1 and y2 of the corresponding homogeneous equation, then we can use those solution y1 and y2 in finding the particular solution of the non-homogeneous equation, given non-homogeneous equation. So after that so this is the formula of particular solution. So in this YP we add the general solution of the homogeneous equation, we will get the general solution of the non-homogeneous equation. So we started with this particular example, find general solution of the second order linear differential equation, which is a non-homogeneous, right? Because the right hand side function is non-zero. This is a non-zero function. So it is easy to check that the corresponding homogeneous equation is this part equals to 0. So that we got, and we know how to solve this equation because it is a second order linear differential equation with the constant coefficients. So we first find its corresponding polynomial, that is m square minus m minus 2m is 0, minus 2 is 0, and the roots are m is equals to 2, m is equals to minus 1. So that will give us this general solution. And yeah, so in this general solution, we have these two functions which are linearly independent and their solution of the homogeneous equation. Right, so now using these two independent solutions, we will find the particular solution using this formula. So we know y1 and y2, we know fx. What is fx? Fx is the right hand side function, this function. This is our fx, 4x square. The only thing we need to find out here is the Wronskian. So Wronskian we have found in the previous lecture that for these two functions y1 and y2, that turns out to be minus 3 times e power x. Right. So this is our Wronskian, and using this Wronskian, now we will substitute everything in this formula of the particular solution, and we'll find what is yp. So what we know is, we know y1 is e power 2x, y2 is e power minus x, fx is 4x square, Wronskian is minus 3 e power x. So we substitute everything here, so we'll get this particular equation. So now next we have simplified these terms. So e power minus x divided by e power x will become e power minus 2x. Then this part will become e power x. So up to this step we have verified in the previous lecture. So now what is the next thing? We need to find out these two integrals. Right. Let us start with the first integral. So if we take 4 outside, then this will become 4 times this function. Right. Similarly, if we take 4 outside of this term, so we need to find these both integrals. So first integral is integral x square e power minus 2x, and in this integral we have two terms, integral of multiplication of two terms, among which the first term, if we keep differentiating, it becomes 0. Right, x square becomes 0 if we take the third derivative. So therefore we are starting with differentiating the first term and integrating the second term. So first term is x square, then its derivative is minus 2x. It's again we take derivative is 2, and then the next term will be 0, right? Because derivative of 2 is 0. And the second term we will keep integrating. So integral of e power minus 2x is e power minus 2x by 2. Again we integrate this function, we get e power minus 2x by and minus 2 square. Again integrating, it will be this term. And then we keep the sign plus, minus, plus, right? Alternate signs. So you may be knowing this formula, but this actually we are using the integration by part generalized formula. Yeah, so we get this one, and then if we simplify, we'll get this all term will become this term. The same way we can find the second integral, that is integral x square e power x. And now we'll substitute both of these integrals value in the yp formula. So substituting both this integral here, we will get this term 4 e power 2x by 3, right, times minus x square by 2 e power minus 2x minus x by 2 e power minus 2x minus e power minus 2x by 4, right? The same way the second integral we will substitute, and then we know that e power 2x term and e power minus 2x term multiplication is 1. Same way e power minus x and e power x multiplication is 1. So using that we will get this term, which is now a polynomial, and if you simplify that we will get this solution. So just we need to take care of the taking the LCM. Yeah, so this is a particular solution of the non-homogeneous equation. Yp is the solution of this non-homogeneous equation. So let us verify that. So if Yp is solution of this equation, it should satisfy Yp double dash minus Yp dash minus 2Yp is equals to 4x square. So we know Yp, we can differentiate it. So derivative of Yp is Yp dash is minus 4x plus 2. Taking the derivative again, we will get Yp double dash to be minus 4, right? So now we'll substitute in the equation. So left side of the equation is this one. So we substitute Yp double dash, that is minus 4, then first derivative and the function itself. So if you simplify, we'll get 4x square, which is the right hand side function of the equation. So that means Yp is basically particular solution of the given non-homogeneous equation. So this verification part is just for our check. We don't need to write in exams. And once we know the Yp, which is a particular solution, we add particular solution in the homogeneous solution. We get the general solution of the non-homogeneous equation. So this we already know, homogeneous part of this given equation solution is this one. So we added Yp in that. We got the general solution of the non-homogeneous equation. Okay, so this regarding the lecture which the example which we have left in the previous lecture. So far what we discuss is we discuss how to solve the second order linear equation, homogeneous equation with the constant coefficient. So today we want to discuss another method, is known as homogeneous equation, which is known as Euler-Cauchy equation. So the equation of the form some constant times x square y double dash plus another constant times xy dash plus third constant times y is equal to 0 Such an equation is known as Euler-Cauchy equation. So here, what is the special thing is that the coefficient of y double dash is x square time constant. The coefficient of y dash is x time constant. Right. So whenever we have such equation, we will solve such equation for x not equal to 0, because yes, let us call this equation number 1. So equation 1 becomes singular if we take x equals to 0. So singular means what? If we take x equals to 0, it becomes cy is equals to 0, and that means we have a trivial solution, y equals to 0. So singular means we get the trivial case. So therefore, the interesting case is when x is not equals to 0, right? So basically, we will consider such. We will try to solve this equation. One for positive x, right? So we are looking for the solution by x of equation 1 when x is greater than 0. That means our solution is defined on the positive real axis, right? Yx is a function defined on positive real axis. And then if we want to solve this differential equation for the negative real axis, then we'll substitute x equals to minus y. So we'll get the solution for the negative x-axis. So let us try to solve this equation using the known method. So what we'll do is we shall apply trial solution. So instead of earlier case, we applied e power mx as a trial solution. Here, because the coefficients are in power of x and x square, we shall trial the solution yx equals to some power of x, right? So again, in this case also, we need to identify for what value of m, x power m is a solution of the given differential equation. So what we shall do is we shall find the derivatives. So y dash is m x power m minus 1. Y double dash will be m into m minus 1 x power m minus 2. And we have assumed that yx is a solution of equation 1, right? Yx is a solution of equation 1. So that means what? That means x power m satisfies the given differential equation. So that means we have ax square, the second derivative of x power m, plus bx times first derivative of x power m, plus c times x power m is equals to 0. So that means x power m satisfies the given differential equation. So now we know what is the derivative of x power m and second derivative of x power m. So we'll substitute these values. So we'll get ax square, second derivative of m minus 1 x power m minus 2, right, plus bx times m x power m minus 1 plus c x power m is 0. So this is the polynomial. So now we can see that this is the equation, and from this we can derive a polynomial, corresponding polynomial, as in the case of e power mx. Yeah, so what we'll do is we will take the term am m minus 1 plus bm plus c common, so the remaining common term will be x power m is equals to 0, right? And we can further simplify this as this part will become am square plus b times m will come here and minus am will come on this side, so that means we'll get b minus a times m plus constant x power m is equals to 0, right? And this is 0 if and only if the corresponding polynomial, which is am square plus b minus am plus c is equals to 0. Why? Because we are assuming we are finding the solution for the positive real axis, that means for x greater than 0. So x cannot be 0, that means this equation is 0 if and only if this polynomial is 0. Right, so such a polynomial is known as characteristic polynomial. Right, so for matrix also we have studied what is the characteristic polynomial that helps in finding the solution. The same way here also we are getting a polynomial that is helping us in finding the solution. So again, in this case also we will take different cases whenever this polynomial has two identical roots, two different roots, real roots, and the conjugate, complex conjugate roots. So let us start with the first case. So if em has two different roots, let us call them m1 and m2. Right. So basically what we started is we started with this equation. We assume that this equation has the solution yx equals to x power m, and by assuming yx is x power m is the solution of the equation, we are getting this equation to be 0. That means the value of m for which x power m is the solution are the roots of this polynomial. Right. The first case is whenever the roots are different, that means m1 is not equals to m2. So in this case we get solutions. So we have two different values of m, that means we get two functions. First is x power m when m is equals to m1, and the second function which is a solution is x power m2. Right. And we know that m1 and m2 are different. So what we are looking for is this is a second order linear differential equation. That means we need to find two independent solutions. So let us find the Wronskian of y1 and y2. So we know that Wronskian is the function and its corresponding derivative. Right. So now whenever we find this determinant, it will be m2 times x power m1 into x power m2 minus 1. So that is essentially x power m1 plus m2 minus 1 minus the second term will be m1 times x power m2 into x power m1 minus 1. So that is x power m2 plus m1 minus 1, right? So this term is common. So essentially we'll get m2 minus m1 into x power m1 plus m2 minus 1. Now what we know in this case, we know that m1 and m2 are different roots of Pm. So that means m1 is not equals to m2. And what other thing we know is that we are taking x is positive, right? So since this is non-zero, x is non-zero, this multiplication is also non-zero because m1 is not equal to m2 and x is positive. So that will give us the Wronskian. In this case, Wronskian of the functions x power m1 and x power m2 is non-zero. Therefore, x power m1 and x power m2 are Li solutions of equation 1, right? So equation 1 is a homogeneous equation, so we don't need to find the particular solution. So therefore the general solution in this case is yx is equals to c1 x power m1 plus c2 x power m2, right? It is c1 y1 plus c2 y2. So this is basically the case of whenever we have distinct roots. So now the next case is regarding the whenever we have repeated roots. So suppose the case when we get repeated roots of Pm is equals to 0. So what does this mean? This means therefore m is equals to m1 is a repeated root of the characteristic polynomial. So polynomial is Pm is equals to so what is the equation? If Pm square P minus Am plus C is equals to 0. This is the polynomial, and since m1 is repeated root, so that means first of all m1 is a solution of this equation. So that means m1 satisfies this, and then we have derivative of this polynomial is 2am plus b minus a is equals to, yeah, so the derivative is this. So that since it is a repeated root, it is also solution of the derivative of the polynomial. So that means 2am1 plus b minus a is equals to 0. So we shall use these two equations in finding the general solution. So note that in this case we have one solution already. Is a solution. Note that in this case we have one solution of equation 1. So how shall we find the second solution? This is a second order differential equation. We know one solution. So using one solution, we can find the other solution, right? So that is the method of reduction of order. So we'll assume that V times y1 is a solution, and then we'll identify what is V. Right? So we shall assume that y2x is equals to Vx times y1x, which is nothing but Vx times y1x is x power m1 is a solution of equation 1. Yeah, so it satisfies equation 1. That means we need to substitute y2, y2 dash, and y2 double dash. So y2 dash will be v dash x power m1 plus m1 v x power m1 minus 1, and y2 double dash will be v double dash x power m1 plus m1 v dash x power m1 minus 1 plus m1 m1 minus 1 v x power m1 minus 2 plus m1 v dash x power m1 minus 1. Right. Okay, so now let us substitute this value of y2 double dash, y2 dash, and y2 in the given equation. So that means we get yeah. So what is the equation? Equation is a x square y2 double dash plus bx y dash plus cy is equal to 0, and we are substituting y2. We are assuming y2 is a solution. That means y2 satisfies this equation. So let us write down this again. It is x square times v double dash x power m1 plus, so this term is coming two times, so that means 2m1 v dash x power m1 minus 1 plus m1 m1 minus 1 v x raised to m1 minus 2 equals to 0. Right. Okay. So now from this equation, just a minute. So this is y2 double dash plus bx times y2 dash. Y2 dash is v dash x power m1 plus m1 v x power m1 minus 1, and the last term, which is c times v x power m is equals to 0. Okay, so now it is fine. So we have substituted all the terms here. So now what can we do now? So we can see that there is some common term in terms of x power m1. So that is x power m1. So x power m1 we can cancel out from this equation, and then we take the other terms common. Then we'll get ax square v double dash plus, right, because v double dash term is this one, we are cancelling out x power m1 plus second term is 2am plus bx v dash. So what are the v dash term? V dash term is this one and this one. So from which we have cancelled x power m1. So the remaining is 2m1 v dash ax, right? So that is the first term, and then dx v dash. All right, and then the last term which we can write down is am square plus b minus am plus c times v is equals to 0. So we can see that this term we can separate as m1 square minus m1, right? And then we can easily see that the last term will become this one. So this term along with this as well as this. So that three terms will give this polynomial. Yeah, and we know that instead of m we have here m1, right? Did I write correctly? Yes, y2, and y2 is in terms of x power m1, correct? Okay. So what do we know here? We know that this m1 satisfies these two equations. All right, so first equation is p of m1 is 0, and that is exactly this equation. So this is 0. The same way, what can we say about this term? So the second equation gives us 2a m1 minus b is equals to a, right? So here we have this term which will essentially become a. So let us substitute all these things. So finally we'll get ax square v double dash plus ax v dash is equals to 0, right? And then we know that x is non-zero, a is also non-zero, because if we take a is equals to 0, this equation will become first order equation, and we are essentially studying the second order method. So we can assume a is non-zero, and essentially we'll get x v double dash plus v dash is equals to 0. Yeah, so what we get is d by dx of x v dash is 0. That means x v dash is constant, and then we get v dash is constant by x. So in particular, we are looking for particular solution. In particular, xc is equals to 1, we get v dash equals to 1 by x, and then solving this equation we'll get v is equals to log x function, right? Again, here also we'll get log x plus c dash. Again, take c dash is 0. So finally we get one particular solution, v is equals to log x, right? Because there for different values of c dash there are different choices of v, but we are looking for only one choice. So that will give us v is equals to log x. So substituting in the equation y2, we get y2 is equals to vx into x power m1, that is log x times x power m1, right? And so now we can check that this y1 and y2 are li. So that is x power m1 log x power m1 is m1 x power m1 minus 1 x power m1 minus 1 plus m1 log x power m1 minus 1, right? And then we simplify this, we'll get x power 2m minus 1, 1 plus m1 log x minus m1 log x. Yeah, so what we can do is we can first take this x power m1 from first row common. Second row we can take x power m1 minus 1 common, and then essentially this will become x power 2 m1 minus 1 times the determinant 1 log x m 1 plus m log x. Yes, m1. Right, and then we know that this last term we can these two terms will cancel out, so essentially we get x power 2 m1 minus 1, which is non-zero because x is greater than 0. Right, so that means y1 and y2 are Li solutions. And so therefore the general solution in this case is yx is equals to c1 y1 plus c2 y2. So that is this one. So whenever we have repeated roots of the Euler-Cauchy equation, homogeneous equation, the general solution is this one. Now the last case is regarding the complex conjugate roots. So whenever we have the characteristic polynomial of the Euler-Cauchy equation, two roots which are complex conjugate, so that means the first root is of the form alpha plus I beta, second root is alpha minus I beta. Where alpha and beta are real numbers. Right. So here also m1 is not equals to m2, therefore y1x is equals to the solution is x power m1, that is x power alpha plus I beta. So what is this? This is essentially x power alpha cos beta plus I sin beta. Right. And the second solution is so that is x power alpha cos beta minus I sin beta. So we can see that in this solution we have I part, but we are looking for the real solution. So that means what we know that from if we have two complex numbers, this one and this one, we can find out the real part and imaginary part. So the same thing we are doing here. So what we know is this y1 and y2 are Li solutions. So why they are Li? Because m1 is not equal to m2. So therefore the corresponding solutions capital y1x, which is the real part, yeah, but what we will do is we will first x power, okay, I have done some mistake, right? Because this is not exponential power. Right, yeah. So you confuse with e power I theta. Yes. So what to do now? Because this is not e power I beta. So that means we should write this x power alpha, x power I beta. So x power I beta we can write as using exponential as e power I beta log x. Right. So x power I beta we can write as e power I beta log x is e power log x power I beta, and that is x power I beta. Right. So that we are using here x power I beta we are writing as in this form. Yeah. So the same way we'll write this term as x power alpha e power minus I beta log x, and these are Li solutions. So therefore now we get the real part. So that turns out to be x power alpha times cosine. Real part is cosine. Real part of this and this is cosine plus the second complex term is x power alpha sine term. That is the complex part. So how did we get cosine theta? We have just added these two terms and divided by 2. So that means we know that e power I times number is cos beta log x plus I sine beta log x, and similarly the other term, and then we have used that. Okay. So we got y1 and y2. What is y2? Y2 is essentially we are taking y1 minus y2 divided by 2y. Right, that is this. Okay. So we got y1 and y2, and we know that small y1 and y2 are Li, then capital y1 and y2 are Li solution. So this part we have verified in the case of the coefficient with a constant, right? So there we verified that if small y1 and y2 are Li, then capital y2 and y1 and y2 are Li using the Wronskian. So these are Li solutions. Therefore, the general solution is yx is equals to c1 x power alpha cosine beta log x plus c2 x power alpha sine beta log x. So whenever we have complex roots of the characteristic polynomial of Euler-Cauchy equation, we shall use this particular method. So let us take one example. So find the general solution of the equation x square y double dash minus 2xy dash plus 2y is equals to x power 3 when x is positive. All right. So what shall we do in this method? How? So first of all, this equation is non-homogeneous equation, right? And the equation is of the form constant times x square y dash plus constant times xy dash plus constant times y. That means it is of the form Euler-Cauchy equation but non-homogeneous equation, right? So what we shall do, we shall first find the solution of the homogeneous equation. the general solution, the corresponding homogeneous Euler-Cauchy equation So the corresponding Euler-Cauchy equation is x square y double dash minus 2xy dash plus 2y is equals to 0. Right. So therefore the characteristic polynomial is so here essentially if you compare with the characteristic uh, standard equation of the Euler-Cauchy, then we get the coefficient of this term is a, so that is 1, a is 1, b is minus 2, b is coefficient of xy dash, and c is coefficient of y, that is 2. Right, so substituting these values in the standard equation, the characteristic equation, and it becomes for this particular value of a, b, and c, we get the equation m square because a is 1, b minus a, b is minus 2, and a is 1, so that means we get minus 3 times m plus value of c is 2. So we get this equation, and if we solve this quadratic polynomial, we get the value m is equals to 2, and the other different value of m is 1. Right, so m1 and m2 are different. So therefore the general solution is of the homogeneous part is yx is equals to c1 x power m1, which is 2 plus c2 x power m, so that is 1. All right, so so one of the function we can call x1, y1, and y2, and this y1 and y2 are Li solution. So now we can find the particular solution, but to find the particular solution, what we need to do is we need to find the corresponding second order equation. So what we have done in this variation of parameter method is essentially we solve this equation, and in this equation the coefficient of y double dash is 1. Right. So first we need to convert when we solve the non-homogeneous part, we always convert the equation in this form by making coefficient of y double dash 1, and then we apply this method. So so for solving non-homogeneous equation, we shall consider so basically we shall solve y double dash minus 2y dash by x plus 2 by x square y equals to x. Right, so what we did is we were given this equation. To make coefficient of y double dash is 1, we have divided the whole equation by x square. So we got this last equation, and now this function is fx. We know y1 and y2. We will find the Wronskian, and then we can solve this equation. Okay, so let me stop here for the today lecture.